So exceptions to the octet rule. Of course, you know, there's got to be exceptions to every rule, right? The octet rule is really nice. It's like, okay, 8 electrons, we're all good with that. And then here we go with exceptions. So there's a couple different possibilities for exceptions. The first one we're going to cover are called free radicals. These are molecules and ions that have odd numbers of valence electrons. So if you have an odd number of electrons, it's impossible to draw a Lewis structure where you have octets for everything and duets for hydrogen. These molecules, the Lewis model predicts are going to be unstable because they don't have octets, and that's true. They tend to be unstable and very reactive. So let's draw the Lewis structure for one of my favorite molecules. No. Right? Nitrogen monoxide. Okay, so we've got nitrogen, and we've got oxygen, and we have to connect them with a bond. And then we have to look at how many valence electrons do we have total. Nitrogen has 5, oxygen has 6. 5 plus 6 is 11, right? So we've got 11 electrons. So we'll try to put these around here. So we've got 2 from the bond, 4, 6, 8, 10, 11. Right? So odd number, we can tell that this is not going to be nice. What we're going to do is we're going to draw the best Lewis structure we can, and that's all we can do. You know, sometimes life doesn't work out the way you want it to. So is this the best we can do? We could make a multiple bond, either double or triple, because here we don't have enough electrons on the nitrogen. We almost have enough for the oxygen, but not quite. So let's try taking one of these lone pairs right there, and we're going to make it a double bond in here and see what we've got. So now this nitrogen has 2, 4, 6, 8, so that's good. The oxygen has 2, 4, 6, 7. So we don't want to have more than 8 electrons here. So what we really have are 2 possibilities. We can give oxygen the full octet and nitrogen a partial octet, or we can do it the other way around. When we've got 2 different possibilities or more possibilities, what do we use to decide which one's better? Formal charges. So we need to look at the formal charges on each atom for each of these structures. Now, I'm not sure how Ms. Henry presented it, but this is how I think about formal charges. So I think of this as being a bit like a corporation where different companies have come together and merged. And now we're going to break it apart, and we're just going to split everything that's shared equally. So I mentally or literally draw a line through the bonds, and then understanding that bonds are each 2 electrons, we look and see if we split this up evenly, how many electrons is nitrogen going to take away? 6, right? 2, 4, 6. And oxygen is going to have 2, 4, 5. And then we're going to compare that to how many nitrogen has as a single atom and oxygen has as a single atom. So the nitrogen, when it came in as a single atom, had 5 valence electrons, right? So, oops, it doesn't work so good. It brought 5 electrons. It's leaving with how many? 6. So 5 minus 6 is negative 1. That's the formal charge on this nitrogen as we've drawn it. Over here for the oxygen, oxygen has 6 valence electrons coming in as a single atom. If we split up this molecule, dividing these shared electrons evenly, we've got 2, 4, 5. So it's leaving with 5 electrons. So its formal charge is plus 1. Does that make sense? So we've got a positive and a negative formal charge. They add up to 0, which is the overall charge on the molecule. So we did our formal charges correctly. So let's do the same for this guy down here. So here, nitrogen always came in with 5 valence electrons. How many is it leaving with now? 5. So 5 minus 5 is 0. So that's a formal charge of 0. Over here, oxygen always brings 6 electrons to the table. And when we divide this up, it's leaving with how many? 6. So 6 minus 6 equals 0. So which is the better Lewis structure? The second one. This is the better one. Lower formal charges are better. If you have to have some formal charges, and sometimes you do, you want to put negative formal charges on the more electronegative element. So this one is definitely not good, because here we have a positive formal charge on oxygen, and oxygen is more electronegative than nitrogen. So that doesn't work out very well at all. So this is our best Lewis structure. That's the best we can do. It does violate the octet rule. Nitrogen monoxide does exist. It's present in air pollution, but it is not stable. It's very reactive, and so it reacts with things like water in the air and does bad stuff. Yes?
So why do you have to put the line in the middle?
You don't have to put the line. Yeah. I just do that as a visual representation of what we're doing. There are different ways of computing formal charges. The book talks about you take the number of valence electrons that the atom has, and you subtract the number of lone electron, non-bonding electrons, minus half of the bonding electrons, and that just seems unnecessarily confusing. I just say, okay, well, let's just look at this thing. We're just going to split the bonds in half and see what everybody's going to take away if we do that. You take what they came in with, subtract what they're leaving with, and that's your formal charge. So the bond, that line is just to help us. Any other questions about this one? So some elements, another way we can have exceptions to the octet rule are incomplete octets. Now these molecules don't have an odd number of electrons, but there are some elements, and they're the smaller ones, that just are okay with not having 8 electrons in their molecules. And boron is one example. Boron and beryllium, we already know that hydrogen has an incomplete octet, right? It's only going for 2. Boron and beryllium are kind of in the middle there. They're the younger kids in the family, but they're not quite the baby, and so they're sort of in between. Boron tends to form compounds in which it has 6 electrons instead of 8. And the way I, rationalize this in my head is, well, it's small and it can't quite handle 8 electrons. That's, of course, not the scientific reason, but it works for me. So let's look at BF3, boron trifluoride, and draw Lewis structure here. So we have to connect the 3 fluorines and the boron, and guidelines tell us that more electronegative elements tend to be on the outside. Things also tend to be symmetrical, and so our skeleton structure is probably going to have boron in the middle and the fluorines bonding to it, rather than trying to have fluorines bonding to each other or anything like that. You may not have gotten this because I wasn't here to lecture this one for you. So if we let's look at fluorine's Lewis structure, just the atom. How many valence electrons does it have? 7. So we'd put 7 electrons around it, and there'd be 3 pairs, and one that's unpaired. That's 7 electrons. This one unpaired electron tells me that fluorine generally forms compounds in which it has 1 bond. So 1 unpaired electron, 1 bond. If we look at carbon, how many valence electrons does carbon have? 4. So we first put them around unpaired, and we don't have to pair anything up. So here carbon has 4 valence electrons. They are all unpaired. That tells me that carbon likes to form 4 bonds.
Carbon and boron, not carbon?
We are.
Okay.
Yeah. I'm just showing you something that you may not have gotten from a previous section. If we look at oxygen, how many valence electrons does oxygen have? 6. So 1, 2, 3, 4, 5, 6, right? You end up with 2 pairs and 2 unpaired. 2 unpaired electrons, oxygen usually makes 2 bonds. So if you look at the Lewis structure for the atom, the number of unpaired electrons tells you how many bonds that atom needs to have in order for its formal charge to be 0. So that can help you when you're trying to figure out how to connect the elements, right? I know fluorine tends to form 1 bond. So I don't want to have fluorine, I don't, keep getting the wrong marker. I don't want to stick the fluorine over here, right? Because this fluorine now has 2 bonds, that's going to give me a formal charge, and I'd like to try to get 0 formal charges. Does that make sense? So I'm going to put that one back. So that helps me come up with this. Okay, so we've got our skeleton. We have to look at total number of valence electrons. So each fluorine has 7, so that's 3 times 7. And boron has how many? 3. So we've got 21 plus 3 is 24. So we've got 2, 4, 6 from the bonds, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we don't have enough electrons to make an octet, but what would we normally do? Make a double bond, right? We could take one of these lone pairs and make a double bond with boron, and then everybody's going to have an octet. We can draw a structure where the octet rule is satisfied. But let's look at formal charges. So actually, let's do the one that's wrong first. This is going to end up being the wrong structure. Here we have octets for everything, so we think this is probably it, right? Let's look at formal charges. What's the formal charge on this fluorine? It came with 7. If we cut everything, all the bonds in half, what's it going to leave with? 6. So the formal charge is going to be plus 1, right? What's the formal charge on this fluorine? It brought in 7, and if we cut the bond in half, it's going to leave with 7. So this one's going to be 0. This one's the same, so it's going to be 0 also. So you can do the cutting and subtracting and stuff, but I can also look at this and say it has 1 bond and an octet, it's going to be 0. Because when fluorine makes 1 bond, it'll have a 0 formal charge. Here's beryllium. Beryllium has 3 valence electrons. If we cut these bonds in half, it's going to leave with 4. It's going to have a formal charge of -1. Now, is this a horrible Lewis structure? No, but we do have formal charges. So let's see what happens if we don't give beryllium an octet. So we're going to take those off, and we're going to put this lone pair back on fluorine. This violates the octet rule. But now what's the formal charge on this fluorine? 0. What's the formal charge on the boron? It brought 3 electrons, and it would leave with 3. So this is a formal charge of 0. So beryllium frequently violates the octet rule by not having an octet of electrons. And if we look at the Lewis structure for boron, how many valence electrons does it have? 3. 1, 2, 3. Looking at that Lewis structure, I would predict that boron's going to make 3 bonds, and that's what it does. Any questions?
Why is it important to have all of those considered here instead of having them off in one person?
Okay, so why is it important for formal charges to be 0? The molecule will be most stable when the formal charges are as close to zero as possible. So when we've got different options for how to draw the Lewis structure, we use the formal charges to tell us which is the most correct. And that'll be the one with the lowest formal charge. Because that indicates a more even distribution of electrons. If you have a negative formal charge, that means that atom is kind of hogging the electron cloud and is partially negative, and then something with a positive formal charge is deficient in electrons. There are molecules and polyatomic ions that have non-zero formal charges. But we're going to look for the Lewis structure with the lowest set of formal charges. Does that help? Beryllium also tends to have incomplete octets. Let's draw the Lewis structure for beryllium. How many valence electrons does beryllium have? Only 2. How many bonds do you think beryllium tends to form? 2. Okay. Because when it forms 2 bonds, its formal charge will be 0. So that's the most likely scenario. So we've got free radicals with odd numbers of electrons, and then we've got these incomplete octets, which only happen for the smaller elements. And then we have too many electrons, expanded octets. So this is a possibility for elements in period 3 and larger. So period 3 starts with sodium through argon. That row on the periodic table, those guys can have expanded octets and any one larger. But those in period 2, nitrogen, oxygen, carbon, fluorine, they never have expanded octets. The reason that we can have expanded octets is that there are d orbitals that are energetically accessible, meaning the d orbitals are only slightly higher in energy than the s and p orbitals, and so we can put some electrons in there, and that's what allows us to have more than 8 electrons. Those elements in the second period, their electron configurations are like 2s2, 2p3 or something. There are no 2d orbitals available, and that's why they never do expanded octets. So let's look at arsenic pentafluoride. So the first thing is to just connect the elements and see how we're going to bond those together. Well, fluorine's more electronegative than arsenic, so we're going to put fluorine on the outside. And fluorine likes to have only one bond. And we can do that if we put all fluorines around the arsenic. Looks a little funky, but sometimes that's how things are. And then total number of valence electrons, we've got 5 fluorines, they each have 7. And then how many valence electrons does arsenic have? 5. So we've got 35 plus 5, so we got 40, right? So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. The fluorines all have an octet. They all have a single bond, and that tells me that they have 0 formal charge. Or you can do the math, cut the bond in half, and you would see that fluorine would leave with 7 electrons. It came in with 7 electrons, so it's got a 0 formal charge. So all of those are 0 formal charge. Then there's the arsenic in the middle. Arsenic has too many electrons around it, right? It doesn't have an octet. It's got 2, 4, 6, 8, 10. It's got 10 electrons. Well, okay, but let's look at the formal charge. How many valence electrons does arsenic have? 5. Here we've got 5 bonds. If we cut all those in half, arsenic would leave with 5 electrons. So it also has a 0 formal charge. So this is okay. This is good. If you do something else, like if you say, well, we can't have 10 electrons in arsenic, we must have to put this fluorine bonded to another fluorine, you'll find out that you cannot draw a structure with 0 formal charges. Arsenic is a big atom, and so it can expand into its d orbitals and form an expanded octet. Any questions? So let's look at sulfur hexafluoride. So again, things tend to be symmetrical, and more electronegative elements go on the terminal positions on the outside. So following that guideline, we'll put the fluorines around the sulfur. We've got 6 fluorines around the sulfur. If we count up the valence electrons, we've got 6 fluorines times 7, that's 42, plus the 6 for the sulfur, that's 48 electrons. So we've got 12 around the sulfur, and I'll spare you all of the counting. You can count to yourself. So there's 48 electrons there. Each fluorine atom has an octet, but the sulfur has more. We call it an expanded octet. It's bigger than 8. The sulfur has 12 electrons. That violates the octet rule, but it's okay. If we compute formal charges, so these fluorines all are the same situation as those. They all are 0 formal charge. If we look at the sulfur, cutting bonds in half, the sulfur would leave with 6 electrons. It came in with 6 electrons, so it has a 0 formal charge. So these are both stable compounds, and this is how they actually are. Any questions? Okay, so this is important. You can only do this for elements in period 3 and above. Okay, let's look at H2SO4, sulfuric acid. This one is a little more complicated because we don't just have one central atom with some things hanging off around it. And it can be confusing as a student trying to figure out how to connect these things. And that's where formal charges come in handy to help you decide if you did it right or not. So let's try putting sulfur in the middle and the 4 oxygens around the sulfur. And then the question is where to put the hydrogens. So we could put them on the oxygens, or we could put them on the sulfur, right? It's possible to put them on the sulfur. But that's not actually where they go. Well, hydrogen's always on the outside. So this is actually how it connects. If you can try putting the hydrogen directly on the sulfur and experiment with that, you're not going to be able to draw a good Lewis structure with 0 formal charges. So let's do this one. We've got sulfur is 6 valence electrons. We've got 4 oxygens. Those are each 6 valence electrons. And then we have 2 hydrogens. Each of those has 1 valence electron. So we've got 42. Anybody? Did I do that right? Math in my head is always 40? 5 times 6 is 40, right? Plus 2, 42. So from bonds, we have 2, 4, 6, 8, 10, 12. Another reason that we might want to do it like this is, how many bonds does oxygen like to have? 2. So if we put the hydrogen on the oxygen, this oxygen has 2 bonds, and so that's probably going to be a good thing. This oxygen has 2 bonds. Here, this oxygen only has 1, so that's not going to maybe work out so well, but you know, you do what you can do. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Am I counting wrong?
It's supposed to be 32.
32. Yeah, see, part of my brain said, this isn't quite right, but 32. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Okay. That looks good, huh? Yeah, question?
So we need a double bond?
We will. We will need a double bond. But this looks good, doesn't it? Everybody's got an octet. Hydrogen has a duet. Yay, we did it. What about formal charges? Hydrogen with 1 bond, formal charge of 0. Hydrogen's always like that. This oxygen has an octet and 2 bonds. So you can do the math. This has a 0 formal charge. This one has a 0 formal charge. What about the sulfur? Sulfur has how many valence electrons? 6. If we cut these bonds in half, it's going to leave with 4, so its formal charge is going to be plus 2. That doesn't sound so good. Plus 2 on the sulfur. What about this oxygen?
Why is that again?
Why is that? Okay, so formal charge, you're going to take the number of valence electrons that the atom has. Sulfur has 6 valence electrons. And then you're going to subtract the number of electrons that it owns in the structure. So what I do is I think of cutting these bonds in half. So 4. Move the lines. So that's minus 4, and that's where I get the positive 2.
If there were lone pairs, would that count?
You count the lone pairs and half the bonds
Or as 2?
as 2. A lone pair is 2 electrons. So we'll demonstrate that with one of these oxygens. So oxygen has 6 valence electrons. And if we break this up, we cut the bond in half. So oxygen gets 1 electron from the bond. And it has 2, 4, 6 from the lone pair. So that's a total of 7 electrons. 6 minus 7 is negative 1. So this oxygen has a negative 1 formal charge. The other oxygen also has a negative 1 formal charge because it has the same setup. So we've got a positive 2 and we've got 2 negative 1s. We would like to see if we can get lower formal charges. Well, the only way we're going to be able to do that is to expand the octet on sulfur. Sulfur is in period 3. It can do that. So what we're going to do is we're going to say, well, this oxygen with a negative 1 formal charge, that means it's got a little bit too many electrons. So what if we take one of these pairs and share it with sulfur? So we'll take one of those pairs and make it into a double bond with sulfur. And this should be seeming like a good idea to us because now the oxygen has 2 bonds, and that's what oxygen likes to do. So now what's the formal charge on this oxygen? It's neutral, it's 0. It has 2 electrons from the bonds, and then we've got 4, 6, a total of 6, came in with 6, so now we have a formal charge of 0 on the oxygen. So that's good. What's the formal charge on the sulfur now? Plus 1. So that's better. But then we've got this oxygen down here with a negative 1 formal charge. We could do the same thing. Take one of its lone pairs and make it into a bond. And then we've got an oxygen with an octet and 2 bonds. That's a 0 formal charge. It gets 2 electrons from the double bond plus its 4 lone pairs. So it's going to have a 0 formal charge. And now what's the formal charge on the sulfur? 0. It came in with 6 electrons. If we cut everything, all the bonds in half, it would leave with 1, 2, 3, 4, 5, 6. So doing double bonds, an expanded octet on the sulfur gets us a 0 formal charge on all the atoms. And this is the correct Lewis structure for H2SO4. Any questions? So this is important down here. Period 2 elements never have expanded octets. They just can't. They're too small.
What do you mean by expanded?
Expanded means more than 8 electrons in the Lewis structure. 10, 12.
Oh, okay.
Yeah. So this sulfur here, this violates the octet rule because it has 2, 4, 6, 8, 10, 12 electrons around it. That's too many. We call that an expanded octet.
Okay.
Yeah.
How did you get negative 1?
How did I get, what, this negative 1?
Yeah.
Okay, that was before when we had an oxygen with 1 bond to the sulfur, and it had an octet, right? So the way I think of these is we're going to cut that bond in half, and so there's 1 electron that's going to go with the oxygen. Whoops. And so oxygen brought 6 electrons to the molecule, and if we have it like this and cut that bond in half, oxygen's going to leave with 7. So 6 minus 7 is negative 1. When we do this, when we've got that double bond and cut that in half, there's 1 electron here and 1 electron there. Now it's oxygen brought 6, and it's leaving with 6, and so it has a formal charge of 0. These structures, when you indicate formal charges, get really crowded if you put zeros all over the place. So a lot of times what we'll do is, if it has a 0 formal charge, we won't write anything. We'll only write the formal charge in if it's not 0. Any other questions? Let's do some practice. Write the Lewis structure for xenon tetrafluoride. Well, the first step is always to connect the elements. Fluorine prefers to have 1 bond, and it's very electronegative, so a good place to start is put the fluorines around the xenon atom. So here's xenon, and we'll string the fluorines around it. Then we look at number of valence electrons. So xenon has 8, and fluorine has 7. There are 4 fluorines, so 4 times 7. That's 8 plus 28, so 36. So if I screw up, just yell at me. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We've got more electrons. We're going to have to do an expanded octet. Fluorine's too small to have an expanded octet, so xenon is not. Xenon is bigger. So we have to put those extra 4 electrons on the xenon. So xenon's going to have an expanded octet.
Why was that again? That you put them on the xenon?
Because xenon is in period 5. Yeah. Expanded octets are possible for period 3 and larger. So xenon can do an expanded octet. Fluorine cannot.
So what if it was chlorine?
If it was chlorine, you could possibly have an expanded octet. But if you drew that out, you'd find out that you would end up with non-zero formal charges. So these fluorines, an octet with 1 bond, you can do the math, but those are all 0 formal charges. Let's look at xenon. So xenon has how many valence electrons? 8. And if we break up this molecule, how many electrons would xenon leave with? 8. Formal charge, 0.
That was 12.
2, 4, 5, 6, 7, 8. It only gets half the bonds. It has 12 electrons. What would that be? I don't know what you would say that is. It's bigger than an octet, right? Fluorine has an octet. When we're counting for octets, these shared electrons count for both, okay? What makes sense to me in looking at formal charges is, well, it's a little bit like, two people getting divorced, and it's like, okay, you take half the kids and I'll take half the kids, okay? Except this is like not a divorce because it's more like a corporation. There's all these people in here, right? But we're going to take these shared electrons and share them equally. You get half, I get half, we're going to go our separate ways. So you look at how much you brought into this thing and how much you leave, and the difference is your formal charge. Does that help? So any questions about xenon tetrafluoride? Let's do phosphoric acid, H3PO4. So this one looks kind of similar to H2SO4, right? So let's put the phosphorus in the middle and put the oxygens, 4 oxygens around it. And then we have to figure out what to do with those 3 hydrogens. So a time saver is to recognize that oxygen likes to have 2 bonds. And so if we put the hydrogen on this oxygen, it's going to have 2 bonds. It's probably going to be happier that way. Let's put the hydrogen over here and another hydrogen on this guy. That's going to make hydrogen happy. Hydrogen's happy with 1 bond. So we'll try that. We've got to add up all the valence electrons. We have 3 hydrogens. They each have 1 electron. We have phosphorus, 5 valence electrons, and 4 oxygens. They're each 6. So we have 3 plus 5 plus 24. What's that, 32? Somebody with a calculator should check my math. Thank you. So we have to have, at a minimum, single bonds connecting things. So we drew in the lines. Each of those lines represents 2 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. That looks nice, right? We have octets for everybody except hydrogen. Beautiful. We have to look at the formal charge. Formal charges on hydrogen are 0. What's the formal charge on this oxygen? 0. It has an octet and it has 2 bonds. That's what oxygen likes. Or you can do the math. It came in with 6, it's going to leave with 6, that's 0. So this oxygen, that oxygen, they're the same. 2 lone pairs, 2 bonds. This oxygen is different. This oxygen has, it brings in 6, and it would leave with how many? 7. So that has a -1 formal charge. Let's make that red. So this one's a -1 formal charge. What's the formal charge on the phosphorus? +1. Because phosphorus has 5 valence electrons, and it would leave with half of those bond electrons, leave with 4, and so that's going to give us a +1. We'd like to see if we can lower the formal charges. The goal is to get them all 0. Not always possible, but get them as low as possible. The way to do that is to look at the negative formal charges and take some electrons away from them and give them to the phosphorus. Phosphorus has a positive formal charge. So we could take a lone pair and put it on the phosphorus, but that would be going too far. So let's just take one of these lone pairs and share it as a double bond with the oxygen, with the phosphorus. So I'm going to get rid of that. We'll recalculate those. So there's the double bond. I still have the same number of electrons. I just moved a lone pair in to be the second bond in the double bond. This oxygen now, 2 lone pairs, 2 bonds. An octet with 2 bonds, that's going to have a 0 formal charge. It looks different than this one, but this one also has 2 lone pairs and 2 bonds. Now, what's the formal charge on the phosphorus? 0. Phosphorus brings in 5 electrons. And how many does it leave with now with the double bond? It gets half of each bond. 1, 2, 3, 4, 5. Leaves with 5, and so its formal charge is 0. This is better. Phosphorus is in period 3, and so it can do an expanded octet. Any questions? Understanding the concept of formal charges and doing Lewis structures is a very important skill for organic chemistry. So some of you are going on to OChem. This is very important in OChem.